Alright, so in this video we're going to cover the net change theorem. And this is really just kind of like an extension of the fundamental theorem of calculus, part 1, where we're just using that difference in the antiderivative to evaluate a total change. So let's write a definition first. So the definition of the net change theorem is that the integral of a rate, specifically, is the net change. Okay, so some different phrases you might hear for this. You might hear it called, or be asked to find the total change, or you might be asked for an accumulation, how much accumulation occurred, total amount at the end, or even displacement. That was probably the first way we really thought about it. Okay, so all of these are kind of phrases that will tell you that this is the type of problem we're working with. And again, we're still kind of using that fundamental theorem of calculus where we're going from A to B. This one specifically is about rates, so we're using lowercase r of t dt. And so that would be the antiderivative of the rate evaluated at B minus the antiderivative of the rate evaluated at A. So this is kind of like the application part of this fundamental theorem. All right, so let's look at some examples. I will warn you, there's a decent amount of writing here involved. Let's just start a new page here. So for example 1, it says at 7 a.m. water begins leaking. That's how every great story starts. Okay, just kidding. That's usually a bad story. From a tank at a rate of 2 plus 0.25 t gallons per hour where t is the number of hours after 7 a.m. How much water is lost between 9 a.m. and 11 a.m. All right, here we go. So it's really not a new process. It's just kind of like problems in context that are specifically dealing with rates. So the first thing we have to decode are the timestamps, right? So if it starts at 7 a.m., I don't know what 7 a.m. is. We're looking at the water loss between 9 and 11. So 9 a.m. is 2 hours later. And 11 a.m. would be 4 hours later. Okay, so first we kind of have to figure that out, because what we're about to do is find an integral. Okay, and we're going from 2 to 4. of the rate, r of t dt. Okay, and then they gave us a specific function for the rate, which was 2 plus 0.25t. So that's what we're trying to find here. So 2 to 4 of the rate, 2 plus 0.25t dt. All right, so actually what I might do in just a moment here is kind of rewrite that as 2 plus 1/4 t. I think that's a little easier to work with, but you know, to each your own. Okay, so the antiderivative of 2 will be 2t, and 1/4 t will become t squared over 2. And remember, we don't have to do plus c when it's a definite integral, but we are evaluating it from 2 to 4. And I'm going to kind of clean that up as best I can here. So that's really going to be 2t. Oh, I just totally left out a plus sign, didn't I? Whoops. And that 1/4, if you have a denominator over a denominator, those just combine. That's just going to be 1 over 8 t squared from 4 to 2. All right, so now we just simply evaluate here. So we're going to get 2 times 4 plus 1/8 times 4 squared minus 2 times 2 plus 1/8 times 2 squared. All right, so it's going to give me 8. 1/8 times 16 is simply 4. No. Yes? No. Yes. No. Wow. I need to get more sleep. That's just going to be 2. Okay, and then this is going to be 4 plus 1/8 times 4. Oh boy. That's going to be a half, I'm pretty sure. So it's going to give me 10 minus 4 minus a half, or I guess 4.5. Let's see. Let's just call that 4.5. And so we get 5.5, and these are context problems. So yeah, 5.5 is an answer, but now we're going to write a statement about it. So let's look at the original question. How much water is lost? And this is in gallons per hour. So we're going to say the amount of water lost between 9 a.m. and 11 a.m. is 5.5 gallons. Nice. All right, let's try a second example. Oh my goodness. All right, so example 2 says the marginal cost so this is kind of like one of those cost, revenue, fun, money problems. The marginal cost of producing X chips, and I assume we're probably talking electronics here and not Doritos, in units of 1,000 in dollars per 1,000. So those conveniently match, so we don't really have to worry about it so much. Is given to us with the function c prime of x equals 150x squared minus 3000x plus 17,500. Okay. So this one has an A and B. So for part A, it says find the cost of increasing production from 10,000 chips to 15,000 chips. All right. So a lot of times companies have to think about things like this because often mass production or larger production will actually lower overall costs. So this is something that they commonly have to think about. So what we need to do here, again, is figure out that change from 10,000 to 15,000. Okay, so we're going to have, and they're in terms of 1,000 units. So 10,000 is really 10. 15,000 is really 15. We're going to find it of that rate function. Okay, which was this lovely thing. 150x squared minus 3000x plus 17,500. Oh, was it t or x? It was not t's. Trying to be consistent here. Sorry about that. All right. And this is one I might cheat and use my calculator for because I'm feeling a little bit lazy and we're going to do a lot of these. And I know if you need to, you can find the antiderivative by hand, but I'm just going to be bad and use the calculator here, and I've already calculated it using Math 9. Okay, so maybe just make a note. We're going to use the calculator. Okay, and I simply get 18,750. So then we're going to put this in context. It's in terms of money. So we'll answer, it costs $18,750 to increase production from 10,000 to 15,000 chips. Awesome. Now let's do part B. Which says determine the total cost of producing 10,000 chips when C of 1 equals 35,000. All right, so this is kind of like those, it's a combination of that fundamental theorem of calculus and solving an equation. So we're going to set it up first because that's the nice way to get this one started. So total cost of producing 10,000 chips. Okay, so that means we basically go from 1 unit to 10 units. Okay, and the reason we're going to use 1, like, why did I choose 1, Miss Wright? Why not 0 or something else? Well, I'll tell you why. Because they gave me 1. So that's going to be the easiest thing for me to utilize here. So we're going to say from 1 to 10 of c prime of x dx equals c of 1, no jk, not 1, the upper limit, c of 10 minus c of 1. Okay? So what they're asking us for is the cost of producing 10,000, well, should I say total cost, so that's antiderivative, of producing 10,000 chips. So right now, our goal is to get this one by itself. So we need to fill in what we know. Now, again, I'm going to cheat here, and I'm going to use the calculator to evaluate the antiderivative of that function from 1 to 10. And when I do that, I get the number 58,950 equals, then I have c of 10, which I'm trying to solve for, and now I can actually plug in what c of 1 equals, which is 35,000. And now it's like solving a really easy equation. So of course we simply add 35,000 over, and I'm going to end up getting 93,950 as the value of capital C of 10, or the total cost of producing 10,000 chips. Okay, so that's like the numerical answer. Now we're going to write our official statement. So it costs $93,950 to produce 10,000 chips. Alright, so we've got one more to go. I know, the real challenge of this video is all the writing that we're doing. You just had no idea what you were in for, did you? Okay, so the velocity of a particle is, and then they give us this equation, v of t equals t cubed minus 10t squared plus 24t feet per second. Okay, so this one also has a part A, part B. So part A says, find the displacement. Over the interval 0, 4, four, 6, and 0, 6. Explain what these values represent. And we're going to cheat and use the calculator again to make this go a little bit faster. So let's set it up. So for the first one, we're going to have 0 to 4 of the velocity function. And again, I'm cheating and putting this in my calculator for v of t. And then I'm putting 0 and 4 as the bounds. And this should equal the position of 4 minus the position of 0. And what I'm getting from the calculator is approximately 42.6 repeating. Okay. And then we're going to say the next one they asked about was 4 to 6 specifically. Still the same function, just different interval. So the position at 6 minus the position at 4. And this one is also approximate, and it's negative 6.6 repeating. And then they want from 0 to 6, so all together. So really we can see where this is going, having already done those first two. Whoops. Okay, and this one is exact because they each had the 0.6 repeating. And we're basically just adding these, right? So the positive plus the negative, and it comes out to an even 36. Okay, so we're going to say the displacement of the particle from 0 to 4 seconds was about 42.667 feet. I'm going to just kind of, it's the same sentence over and over again, so I'm going to say 4 to 6 seconds was negative 6.667 feet. And then 0 to 6 seconds was 36 feet altogether. Okay. It's kind of like 3 of the same sentence over and over again. Okay, and then part B is very closely related, but it says find the total distance. Traveled from 0 to 6 seconds. Alright, so remember, if there's any possible negatives here, or negative areas, which there clearly are, we're going to take the absolute value of that function when we type it in our calculator. And so whenever we kind of look at where we're coming from up here, if we, instead of making this negative, if we kind of made this back to a positive area, it's like we're adding this and the absolute value of this together. So your calculator should give you approximately, approximately 49.3 repeating as a result, which again is simply this original area and then plus this second area. So it should kind of make sense that that's what's happening in our calculator when we ask it to do that. Alright, and this will conclude our video on net change examples.